Okay, so welcome back to 10.4.18.6.18. So today we're going to pick up where we left off, talking about map inference with mixed integer linear programming. And this time we'll actually get to see how the sort of ILP framework that we had set up last time can actually be used to solve the problem that we care about. And then from there, once we've actually established how you can do map inference, we'll see how you can use map inference as a subroutine within learning. And our first example of that is going to be structured perceptron, which is what we'll discuss today, which is one of the probably simplest actual learning algorithms that we'll look at in this entire course. It's beautifully simple in the way that perceptron is simple. Okay, so questions. Let me throw one at you rather than the other way around. What is the study on supporting and improving teaching at the university level that I just mentioned on a Piazza post? So rather than me answer it, why don't I let Francesca do just that?
I'll answer this question for you guys. Hi everyone, my name is Francesca. I'm a fifth-year PhD student in the Human Computer Interaction Institute. I work with Dr. Amy Ogren, and my team and I are very interested to run a study in your classroom, which is why I'm here today to get your permission to run the study. We have been running studies like this for the past 4 years and have extensive experience in this domain and the education domain. So before I tell you more about the study, I need to ask if there's anybody who's younger than 18. Do we have any minors in the class? Awesome. So the study will take no time for me except for the time that I'm talking right now, because the focus of the study is actually your professor and not you, the students. The research study details are as follows. There's going to be a study team member present in some class sessions. The study team member will sit somewhere in a corner taking notes. They won't interfere with class. The classroom you're currently in is an instrumented classroom, which means that we have a sensor over there and a sensor over there. We don't start those sensors unless we get permission from everybody in the class to do that. We will process, once we get your permission, we want to turn those sensors on, and we do audio and data video collection. And we process this data to get features such as how many students raised their hand, was your professor standing on the left side of the classroom or the right side of the classroom. And we actually use machine learning for that, the OpenPose library, if you're familiar with that. If we get permission from everybody in the class, the data collection is going to start automatically on schedule at the beginning of the class. The information we collect is going to be confidential. We will not attempt to check or personally identify any of you, so I won't know who you are in any way, shape, or form. The data we will report in papers and presentations is going to be high-level data. The data will be stored in a very secure server at CMU for a minimum of 3 years past study completion. Annotation services might be used to transcribe video recordings of classroom sessions. Transcriptions and annotations will be crowdsourced. The sponsor of the research, the National Science Foundation, may have access to the research records. So just to reiterate, we're not evaluating anybody with this data. The data is not going to be used to evaluate you or your learning or your performance in this class in any way. As mentioned, the focus of the study is your professor and not you, the students. Whether you participate or not, this will not affect your grade in this class in any way, either positively or negatively. Participation is voluntary. In addition to that, if you agree now to the study and then later decide you don't want to do it anymore, you can email me. My email is in the Piazza post, very likely. And once we get notified from you that you don't want to continue the study, we can stop at any point immediately. And that's it, pretty much. So, any questions before I get your permission? Anything that I can answer very quickly about our study? Awesome.
So maybe I have
I'll
ask a question on your behalf. So what would the data that you're collecting actually look like? Like what would you actually be storing on a server?
So we actually do store the video and audio data, but the data that we work with is this kind of data. If you have walked in Newell Salmon Hall, the OpenPose library is displayed in one of the screens over there. We get joints and segments of each of your bodies, including your professor, and we actually mainly focus on the movement, the gesturing, position in the classroom, and things like that. We don't. If we get data from the students, we do things like how many students raise their hands and not who raised their hands. Like 15 out of like 30-something students raise their hand. That kind of information is what we work with. Yeah.
Questions from you guys?
Any other questions? Anybody wants to work? Oh, absolutely. You should ask your professor for that, not me.
But
okay.
They would be tracking you eating it.
Actually, our algorithms are not that advanced, so we wouldn't be able to, unfortunately. So if you agree with us running the study and recording the sensor data as I described, please raise your hand. I'm sorry to make you do this, but the Institute Review Board requires us to ask you to raise your hand. If you do not want us to run the study, do not raise your hand. Oh, if you agree to the study, please raise your hand. Let's go with like a positive. I see some people have not raised their hands. Okay, so then we're not running the study in this classroom. Thank you so much for your time. I hope you have a wonderful semester. Thank you, Professor Roman.
Okay. Great. So next question. This is a more important one. Do we really have to write a project report and create a video presentation? It just seems like so much work. No, actually. We thought about this, and the syllabus is included sort of all of the traditional components of a project, but the more we thought about it, the more we realized there's actually, I think, a much more streamlined way for you all to communicate to us what you are doing at 2 points in the semester, which is really what we want to happen. Okay, so the new milestones for the project in this course are going to consist of a midway poster and a final poster, which replace the midway report and the final report. You'll still submit a sort of standard text proposal before either of those. But the idea is that the midway poster session will happen on Monday, November 25th, and the time not being announced here is just because we have to actually have confirmation of a room before we can announce it. And then the final poster session will happen during final exam week, again, like pending confirmation on a space. And the idea of this is that usually the process is sort of you're submitting a midway report, and then we read the report and like write you some feedback. So our thought is that having something interactive where we can actually have a dialogue with you is actually going to be a better way for us to give you feedback, and that's why we're going to do this midway poster session. It will most likely not involve you printing a poster midway. Rather, we'll probably do something kind of where you're just projecting your whole poster on a screen. This is sort of maybe like to be finalized once we, again, have a space finalized. And then for the final poster session, we would actually use sort of the traditional poster printing for that and hold it in the usual way. So this has an important consequence, which is in order to hold a final poster session during final exam week, we can't still have a final exam during final exam week. This is both because it would be just like condensing the schedule a lot for you guys, but also just for sort of the usual university policies. So what this does is just the final exam will be in the last week of classes on Thursday, December 5th in the evening. And so for 10-418 students, that's sort of your last obligation, and that final exam. And then you won't have a final exam during final exam week. So obviously this sort of dramatically changes the flow of the course. The final exam, we won't be able to, there's going to be like some topic in that last week of classes that just won't be covered on the final exam. But we think this is going to dramatically improve your experience with the course in a way that sort of allows you to get more sort of direct feedback from us, and also save you from this sort of laborious process of technical writing, which is not really kind of our goal for the outcome of this project, where what we want is for you to be communicating, your sort of experiments and your results, your models and your setup, and we're less concerned with your ability to clearly write a report, which is often, and so there's just an additional note here, which is that I think from an assessment perspective, it's very difficult to assess the quality of a report, because it's often very, like the assessment of the report quality is often colored by the quality of the writing. So if you have a lot of technical writing experience, then you can make a really lousy project sound really good. And likewise, if you don't have that experience, it's actually very difficult to always kind of compactly represent everything that you did in a constrained space. So we think this will work a lot better, and then most likely, So again, I have to sort of still say at this moment that like poster session is during this time frame, but most likely we're looking at December 11th for the poster session. So I think our original final exam wasn't scheduled till December 13th, but don't actually. So we won't. Oh, sorry. So we won't go past December 13th, whatever our official final exam schedule said. So when booking flights, we'll try to nail down this date, maybe even this week if we can, so that you guys are able to take that into account. Any questions about this? Yeah.
If there was an obligation of traveling before the final poster session, since there is a teamwork, how would we deal with that?
Oh yeah. So let's talk after class. We'll basically like so for example, this is like really close to the NeurIPS conference, which I'm. If any of you are going to, you can go check out my paper there, but I'm not going to be there. So, you know, I think that we have like someone who is planning on attending said conference, and we'll figure out how to make it work. So I think it sort of depends on like the exact dates that that the travel works with. So, any other questions? Oh, there's one other important detail. So the schedule is also updated because of all these changes. Then we were also able to adjust the timing for homework 3 so that it's a lot more sensible. So right now homework 2 is due on Saturday, and then you just have this break leading up to the midterm exam next week, and then homework 3 won't be released until after the midterm exam, so that you don't have to worry about it in the meantime. Okay. Great. So last time we talked about linear programming, integer linear programming, and we left off with this discussion of branch and bound. And so that's where we're going to pick up today. And so we had been thinking about branch and bound, specifically in this setting where we had been thinking through the sort of behavior of branch and bound in terms of the global upper bound and the global lower bound that it maintains during its runs. So what I want us to think about now is this picture of what branch and bound is actually doing as it sort of proceeds through these individual steps. So the idea here is that, as before, we're trying to solve some ILP, and so that's going to be some max over C transpose X. This full screen, such that AX is less than or equal to B, and so this is the linear part, and then we have each of our xi's for all I is greater than or equal to 0, and then lastly that xi is integer. So inside of the setup, we're going to think about a specific example here, like one of the ones that we had been thinking about before, where we assume that we've kind of discretized the space of points. And what we're searching for is the actual optimum within this set of points. And so the actual LP relaxation is going to look something like this. And we could say then that our objective function, C transpose X, corresponds to a vector pointing in this direction. And so crucially what we observe is that the LP op is at the top corner of that blue rectangle, whereas the true opt of the ILP is this top point. And so the idea of the branch and bound algorithm is that it proceeds by constructing a branch and bound tree. And in the first step, what it needs to do is actually pick one of the two variables, x1 or x2, and it needs to branch on that variable. So what we would find is that it runs, so this is going to be the first node in the branch and bound tree. And at that first node in the branch and bound tree, it's going to run the simplex algorithm to get back a value of the current linear programming relaxation. And so when it does that, what it will find is that the global upper bound for this problem is going to be the corresponding to the actual solution for this top red point. So we could call this some x2 prime and x1 prime, and we could say that the sort of the global upper bound here is equal to C transpose x1 prime, x2 prime. So once we have that upper bound, we also have a solution to the LP, right? But as we can see from our picture, x1 prime is not in the set of integers. And so what we might do is we might say, well, for that reason, we're going to branch on the variable x1. And we're going to look at two possibilities. So if we said that, say, x1 prime is equal to, say, 2.8, then branching on that variable corresponds to dividing into two subproblems. One would be x1 less than or equal to 2, and one would be x1 greater than or equal to 3. So when we branch on this variable, we're effectively creating two new subproblems. So our original subproblem had just the set of constraints ax less than or equal to b. But when we branch, we're creating a new linear program that now has the feasible region corresponding to this green LP that keeps everything. So here we have values 1, 2, and 3. So in this green LP, we capture everything that is x1 less than or equal to 2. And then in, say, this rainbow LP, we capture everything that is, oops, sorry, it's not quite right. So the rainbow LP is going to be cutting right through the value x1 equals greater than or equal to 3. Okay, so now on the left side, we're just going to explore the green LP. Okay? And if we solved it, we would get back a new solution to the LP, this time giving us back x2 prime prime and x1 prime prime. So here, for the green LP, our upper bound is going to be given by C transpose x1 prime prime, x2 prime prime. And so this time, what we observe is that x1 prime prime, it looks like is actually going to be integer, right? Because it got pushed all the way up against that region, that side. And so if we were to branch, it would be on the variable x2, where x2 landed somewhere between the values 3 and 4. And so we would branch down one side with x2 less than or equal to 3, and on the other side with x2 greater than or equal to 4. So this would give us 2 new nodes, okay, and 2 new LPs. What would happen on the x2 greater than or equal to 4 node? So we would solve a new linear program. It would have these 2 new constraints, x1 less than or equal to 2 and x2 greater than or equal to 4. And what would the solution of that LP be?
No solution.
No solution. It would actually return infeasible. Because for this one, when x1 is less than or equal to 2, there does not exist any point with x2 greater than or equal to 4 that is in the feasible region. Okay, so this is what branch and bound does. It gradually subdivides the space, as we saw last time. And for each of those partitions, it's gradually finding solutions to the actual LP relaxation of the original program. But as you divide more and more, you're gradually tightening those relaxations because the actual relaxations are getting closer and closer in. So eventually, if you subdivide on every variable all the way down, you would get back a bunch of LPs that are restricted to individual points. So once you have either an integer solution at one of the LP relaxations or one of those individual points, then you can know that for that particular subtree, the global and the global upper bound, sorry, the local upper bound and the local lower bound are equal. Okay, so that got corrupted. Okay, well, okay, so we're gonna skip the actual description here. Maybe it's something that I'll double back to. So this is just again, sort of a picture of a branch and bound tree, where now you can imagine we have some root node, and we divide into 3 subproblems by branching on some variable. Yep.
Is this for convex and non-convex surfaces or just convex?
Oh, good question. So whenever we're working with an integer linear program, remember that the only valid solutions to the original integer linear program are these individual blue points. so so technically speaking, this is a non-convex problem. But it's sort of a strange non-convex problem. It's not, so we're used to talking, usually when we talk about non-convex, say if we have a function, if we have x here, and we have some function of x that is non-convex, we might say f of x is a non-convex function of x. Okay, now let me draw a different non-convex function of x. So this is f prime of x. So f prime of x is also a non-convex function. Oh wait, actually, sorry. Let's add one more point just so we're. So f prime of x is a non-convex function of x, but it's also not continuous. It's not smooth. It's just it's only defined for certain values of x, and so it's definitely not a convex problem. And so in general, we have this for all of the integer linear programs that we're going to work with, that they're going to be at least non-continuous, non-smooth problems. The sort of caveat that I should throw in here is that you could actually define a problem that is a mixed integer linear program, where it is convex in the non-integer variables, but it's non-convex when you're looking at all of the variables, because of this sort of these discontinuities. So in general, the branch and bound algorithm, this was a very long-winded answer, but the branch and bound algorithm is for non-convex functions.
So does that mean like the upper bounds that we find are local and not for like the entire space that we're looking at?
Yes, exactly. So when we got when we solved that green LP, okay, we got this upper bound, C transpose x1 prime prime x2 prime prime, right? And that value says that an upper bound on how well you could do inside this green region, if you were to impose the integer constraints, must be whatever this dot product was. And it makes sense too, if you think about higher values of the objective function going in the direction of that arrow, then the true optimum within that green region is this top point. And so in that case, the bound is actually tightened, right? So the upper bound at the root node of our branch and bound tree was all the way up at whatever that red node is. And for the side where x1 was less than or equal to 2, we actually got tighter on that left side. And if you look at the right side, which we kind of skipped here, but the rainbow side, here's the optimum on the rainbow side, and it also went down a little bit. And so the upper bound actually went down because it was going to be the max of the green point and the rainbow point. Okay, so the whole idea here is that we have this lovely situation, which is that when you subdivide into these problems, you're suddenly able to prune away subproblems. And so here, the yellow nodes are the solved subproblems, and the red nodes are pruned subproblems. And the green node is a feasible solution, meaning that we actually found an integer solution to the original ILP. And so when we have a pruned subproblem, that must have meant that we found some point along the way which had a better score than the upper bound for that subtree. So going back to our example, we could actually see this happening where, suppose we had, before going down and subdividing on the green LP, suppose that we had instead first gone down the rainbow side. So on the rainbow side, it might have been that we would get lucky and we would find the, so as soon as we subdivide on the rainbow side, we're going to subdivide, say, x1 less than or equal to 3 or greater than or equal to 4. As soon as we add that constraint, then suddenly we're going to find, let's actually sketch this out. Just need a little space to do it. So over here, so if we had subdivided this rainbow LP first, and we had done so on x1, then what we might have done was say, okay, on this side we're going to say x1 is less than or equal to 3. And on this side we'll say x1 is greater than or equal to 4. So now we need a couple points shown here for the case where x1 is greater than or equal to 4. But what happens when we actually subdivide this rainbow LP? Well, the LP on the left node, let's call it the magenta node here, becomes simply a line ranging through here. And then on the right side, we're left with, say, a green highlight, which is going to be this region. So once x1 is less than or equal to 3, suppose we, at this node, got back yet another fractional solution, because x2 is still fractional. So at that moment, we might try to convert it to an integer solution by, say, randomly rounding the resulting value. So if we got back a solution at that node, it would potentially be the true optimum. And once we have that true optimum, it's actually slightly higher than the upper bound for this side. So once you have a solution that has that objective score that's higher than the objective for this entire subtree, all of the nodes in this subtree we can just prune away. So the important note here is that the question is sort of which comes first. So if you had chosen to do a lot of exploration and subdividing in this green LP subtree, you might have done a lot of work calling simplex over and over and branching on different variables. But if you had instead gone down this branch and found a feasible solution quickly, then you might have been able to prune out that entire branch early on. So then the remaining question is, how do people actually do all of this? And the answer is lots of heuristics. For choosing things like which variable to branch on, and which node to explore next. Etc. So, okay. Oh, so here's just sort of another picture of sort of a simplified version of what we just talked about. And so, yeah. Okay, any questions just while we're here? Yep.
So you said if we did the rainbow side first, wouldn't we still need to do the green LB the whole way down just to realize that there is no feasible solution that is higher than? I mean, we won't be able to pull it unless we know that there is no other feasible that is maximum that is higher than the rainbow LB.
So let me actually attach some numbers here because I think that actually makes it a little easier. So suppose we have a feasible solution on the magenta side such that C transpose X is equal to 8. Okay, so that's going to be some feasible solution that shows up here with C transpose X equal to 8. Okay. Now, suppose that the upper bound that we came up with for that green LP was C transpose X equals 6. Okay. So what is this upper bound telling us? This upper bound is saying the best that you can possibly do, subject to the constraint that x1 is less than or equal to 2, is an objective score of 6. So any solution you find in this subtree will not have a score higher than 6. Okay. A feasible solution tells us that we already know that we can do at least as good as 8. Okay. So once we have this feasible solution with value 8, we can say, well, 8 is higher than 6, and so we don't need to look at anything in that green subtree anymore. So that's the real power of the bound part of branch and bound, that we can, because we have these bounds at each node, and if we have found good solutions along the way, we might be able to completely get rid of entire regions of the search space. Yeah?
When you say that we have heuristics to choose which variables to branch on, does that include the initial root node?
Yep. Yeah, so the way that we would typically do this is we would run the simplex algorithm, and then you might, so a good heuristic, for example, is pick the most fractional variable, the one that is farthest from integer. So if you get some variable that has value, not 2.8 but 2.5, that's as fractional as you can get, right? So that would be a good one to pick.
And so then, like in this case, we picked the one that happened to enclose the true optimal, but that might not necessarily be the case, right? Like less than or equal to 2 or greater than or equal to 3 actually encapsulates the true optimum, but like, are we given the true optimum to start with, or are we just trying to approximate it using IO?
No, so we're trying to find the true optimum. And really what we're going to do at the end is try to also say not just like that we've approximated the true optimum, but if we run this thing to completion, at the very end we'll be able to say this is definitely the true optimum. And we've proven it by pruning away all other parts of the tree and shown that they're all going to be worse than this optimum.
But I thought that the true optimum are decimal values, and we're only working with integers. So is this the true optimal integer solution?
Yeah, true optimal integer solution. Yep. So we're always trying to find an integer solution. Great. Any other questions? Yeah.
So how do you decide which xi to branch. So in the first node, you divide on x1, and on the left side you divide on x2.
So again, we go back to heuristics here. So the one that I mentioned, the most fractional variable, is often a good choice here. It depends on. So you can also look at not just most fractional, but you can look at, within the simplex solution, which of the variables was least close to a collection of constraints. So in your simplex solution, you can actually know whether or not one of the, like how many of the constraints were actually tight, meaning we have these less than or equal to constraints, so we call them tight if they're equal to. So you could look at variables that are not tight, meaning many of the constraints don't apply. And so maybe that's another good variable to branch. So the way that people come up with these heuristics is to look at lots of different options and see which ones are actually like fast to implement. That's usually the trade-off. And basically, there are companies like Cplex and Gurobi that spend, thousands of hours of engineer time trying to figure out what the best heuristics are. And then they sell their mixed integer linear programming solvers to people who need them, like for example, airline companies that need to schedule a bunch of planes. Okay, so we're not an airline company. We want to use this for map inference. So remember, we kind of had this third inference problem, and we said that the first two were sharp P hard. This one is a combinatorial problem, and so it is actually NP hard in the general case. And so the goal here is that we're going to want to predict the highest likelihood structure, some y, given our observations x and say parameters w. Okay, and so the key idea here is that we're going to reformulate this problem as an integer linear program, and then essentially for most problems this is going to be sort of a new way of writing down the problem. And then we're going to remove the integer constraints and solve, say, a linear program, and that would give us a relaxation of it. Okay. So here's the lovely other side detail. So if you did remove the integer constraints and you found that there was a unique map assignment to the LP relaxation of the ILP above, then it's actually guaranteed to have an integer solution, which is exactly the map solution. Okay. And if that doesn't work out, then our otherwise here is run branch and bound. Okay, so what we're going to do is we're going to think about how we could do this for the case of a Markov random field that is going to have binary variables and pairwise potentials. Okay. So here, so our first example of map inference for ILP is going to be a binary pairwise NRF. So for this setting, we're going to assume that what we want to do is work with a model where all of our variables, say y, are binary. So there's 0, 1 variables, and we could say that we have, say, t of them. And then x is just some arbitrary input vector that we're conditioning on. Oh, and actually, sorry, we're going to do an MRF here. We won't do the CRF. So we'll just ignore the fact that x is there, and we can always fold it back in if you want to see the CRF. So here, we're going to say that the probability of our vector y is given by 1 over z and so this is going to be some function of our parameters theta. And we're going to have a product from t equals 1 up to capital T. And for each variable, we're going to have one potential function. So that's some psi t of yt. And then we're also going, because this is pairwise, we're going to say we have a product over all st pairs in some edge set defined by our graph, so that we have a potential psi st of ys yt. So this is going to correspond to some undirected graphical model. It looks something like this. And the key thing to note here is that even if we did have parts of the actual undirected graphical model where we actually included a maximal clique that had more than just two variables in it, like this maximal clique y2, y3, y4, we would still only have potential functions for each of these edges, y2, y3, y2, y4, and y3, y4. Okay. All right, so this is our pairwise MRF, and now what we want to do is say that we can instead work with a slightly different form of this, because we know that all of these potential functions are non-negative. So let's actually here assume that psi st ys yt is defined as the x of some score function. So our score function will just be some phi st of ys yt. And then similarly, we'll have potentials on the variables yt that are defined as x of some phi t yt. So you can think of this like what you're doing for homework 2, where the phi's are, say, the output of some LSTM or something or other, and we're concerned with exponentiating them to get back something non-negative. And so in this case, y is just going to be, or rather we can now write the log of d theta of y as a sum over t for all psi t or phi t of yt plus a sum over each of the edges, which are the st pairs in an edge set E of phi st ys yt minus some log z. Okay. So let's suppose finally that what we want to do here is say that we're trying to set this up as an actual ILP. So here, our goal is to find some y hat that is the argmax over all possible y's for the log probability of y. So if we want to set this up as an ILP, then we're going to need some objective function. So the objective function is going to be a linear objective function. Remember, we're maximizing over values of y. So what should our objective function be? We want it to be linear in y. Let me give you a little bit of a hint here. So suppose that we can actually index into these little phi factors. So how are we going to do that? We'll say that phi tk is defined as phi t of k. And similarly, phi st kl is defined as phi st k. Okay, so these are now real value numbers, right? This is a scalar, this is a scalar. Can we somehow use those to set up an objective function that is linear in y? Okay, let's push on a little bit here, see if you guys can fill in the details. So suppose what we have is a sum from t equals 1 up to capital T, right? And for each of those, I'm going to take, so remember we're maximizing over y, and we're going to say for each one of these, we're going to have the value of yt, and we're going to multiply that by phi t comma yt. Right, which is one of the entries in that vector. Okay. So if yt is equal to 1, then what do we get back?
Isn't phi t belongs to yt?
Yeah, phi t of yt.
So
Okay, but what if yt is 0? What do we get back? 0. That's not good. So how can we get back something more informative than 0 when yt is 0? Yeah, 1 minus yt. Okay, so let's do plus 1 minus yt here times phi t, let's see, what's this going to be? So it's going to be 1 minus yt times what? 1 minus yt in the subscript. Okay. Okay, so far so good. So this here is our first term, and then we can do the exact same thing for the second summation. So we're going to sum over all edges st in the edge set. And now, things are going to get a little more annoying. So we're going to say, so I'm actually going to rewrite this, we can still do it the same way. So we're going to have ys yt phi st. And now, I think just so that our brains don't explode here with subscripts, I'm actually going to change our notation just a tad here, so that we'll say phi t of. We'll go ahead and stick with what we've got. Actually, you know what? I'm not sure. So I think that this idea of vectors is helpful, but I'm not sure that it's actually really going to help you conceptually. So let me just go back here and just say, just use the original function that we had. Just call this on the value of, no, I guess I don't want to do that. Sorry. Okay, so we'll just plot along here. So here we're going to say subscript ys yt, and then plus 1 minus ys yt times phi st 1 minus ys yt plus 1 minus yt times ys times phi of st ys 1 minus yt and plus 1 minus ys 1 minus yt phi of st 1 minus ys 1 minus yt. So this sort of ridiculous way of writing things out shows for us a really important detail, which is that we can take this entire thing and write it out in terms of little binary variables. Okay? And this way of writing it out is entirely linear. Okay? So what are the constraints? What constraints do we have on the variables yt? Yeah, just that yt is in 0, 1 for all t. So that constraint that they're 0, 1 valued is sufficient to ensure that the max of this is the max likelihood assignment to the variables.
Is capital T the number of nodes?
Yep. So this is just the number of variables. Okay. Okay, so here's the next question. What if yt comes from, say, a set 1 up to k? Can we still do this? Is this still going to work?
I have a question about the constraint.
Oh, sure.
This does not correspond to the linear program constraint that we discussed earlier, right?
Oh, yeah, so a good question would be, how do we get this to look like the standard form that we had before? Okay, so the objective is fine. So the objective is already some linear function of y. Okay, check. Now, what we need is constraints, thank you, constraints of the form ax less than or equal to b. Okay, so to get those, we could just say yt is less than or equal to 1 for all t. Okay. We could write that down in matrix vector form as the identity matrix times the vector y is less than or equal to the vector of all ones. So this is equivalent to identity matrix times vector y less than or equal to a vector of all ones. Okay. And lastly, we already usually have the constraint that each yt is greater than or equal to 0. And then the last constraint is just that yt comes from the set of integers. So this is exactly equivalent to our original constraint set. But now it's in standard form. Yeah.
Can you explain more about why this is a linear function of y? Because to me it seems quadratic, like when you have a ys times a yt.
Oh, yeah, so we did write it wrong. So it is quadratic. So, let's see, where did I go awry here? So we want to encode the constraint. Okay, so this is a wonderfully important detail. So, question. How to encode, say, yt times ys, or yt in 0, 1, and ys in 0, 1 as a linear function. Okay. So here we can turn to some lovely tricks that only work if yt and ys are binary. So namely, we need that, so let me make sure this works. So let some new variable yts be defined as the product ytys. And now we need linear constraints on WTS such that it only has value 1 when these both have value 1. So how could we pull that off? Okay, so the first one is WTS needs to be 0, 1 valued. What's the next one?
WTS is 1 when YT and YS is 1.
Yeah, but how can we get that as a linear constraint? Because, I mean, that's what we really want. But saying it in words is one thing, writing it down as a linear constraint is another.
Can you use an AND oscillator?
Yeah, it feels like we need an AND. How can we get AND? Maybe just add 2 constraints, like WTS is greater than or equal to YT, and WTS is greater than or equal to YS. Okay, so this would ensure that that WTS is greater than or is only 1 when both of these are 1. How could we ensure that WTS is 0 when either of these is 0? This is an OR problem. This one's a little trickier. So addition is kind of like, in many cases in these sorts of programs, addition often functions a lot like an OR. I'm trying to think of how you might get something like this.
It's greater than or equal to YS plus YT.
Yeah, so if we say WTS is less than or equal to the sum of YT plus YS. Does that work? No, not quite. So if they're both 0, then it works. But what if only one of them is 0? Then it's just WTS less than or equal to 1. So how can we fix that? Yeah, just divide by 2. Voila. Okay, so now we can go back to our original program and and substitute in these little YTS variables everywhere that we had the quadratic variables. So, okay, so solution here is just going to be substitute a WTS variable for each YTYS. And this gives a linear objective. Okay. Great, that would have been egregious if you hadn't asked that question. We would have been all wondering what happened to the linear objective. Thanks for asking. Okay, so now we didn't actually go back and answer my earlier question, which was, so what if yt is in 1 to k? Can we still do this? Okay, let's take a quick look. Okay, so I want to look at a particular example here of optical character recognition, where we're going to say our output is a sequence of characters, and our input is going to be some x, that is individual images of characters. So y is just characters A to Z for each time step. And here, what we're going to say is that, did all of my slides? Okay, so this slide is just describing the actual structure of the CRF for the OCR. And again, it looks like I'm getting some weird issues with my slides today. So basically, here what we're looking at is just, these are just our potential functions at the top, and we're defining the potential functions here in the usual log linear way. So you can think of this just like a linear chain CRF. So if our output y is a sequence A, B, A, B, B, then we could use one variable for each time step as an indicator variable for the corresponding class. So here, what we have is Z1, so M here is the actual value, so Z1 of M is going, so this is M. So if M is equal to A, then we get this vector with a 1 in the A position and zeros elsewhere. And if M is equal to B, we get a 1 in the B position and zeros elsewhere. And then if M is A, and then B, and then B, we get this sequence of vectors. Okay, so then we can also have indicator variables for each pair of variables. Right? So this would be an indicator for M equals A and N equals B, right, where we have the value 1 in that position and 0 everywhere else. Okay, and then so on down the line, and now we can look at each pair. So this was AB, this was BA, so it has a 1 here, this is AB again, and this is BB. So now what we can do is we can rewrite the actual optimization problem in terms of these indicator variables. So what we have is that we're going to have sort of two types of potentials. We're going to have node potentials and edge potentials, just like we did in the binary pairwise case, but now we're no longer binary. So now we can say for every variable, j, and for every possible value that that variable could take on, m, we're going to multiply some binary indicator variable times our potential function. And then we'll do the same thing for each pair of variables, jk, and for each pair of values that they could take on, mn. And we multiply that by the edge score. And then lastly, we have constraints that the indicator variables are going to be greater than or equal to 0 for these two cases. So we have this additional constraint here that sort of corresponds to what we were doing with these little W indicator variables, which is we have a normalization constraint that says the sum of all of these little indicators for a particular j needs to be equal to 1. And then similarly, we have to have agreement between each of the indicator variables for a variable and the indicator variables for the pair of variables. Okay, so this is saying that the sum over n for zjk is equal to the value m. Okay. So basically, we could look at that as this, the sum of this column needs to equal 1. And the sum of, or sorry, this row needs to equal 1. The sum of this second row needs to equal 0. The sum of this other row needs to equal 0, and so on. And then you have the same constraint for the columns as well. And then lastly, you have that these indicators are integer. Okay. And because we have both the normalization constraint and the greater than or equal to constraint, that's going to make sure that they're integer values in the range 0, 1. Okay, so if you kind of conceptualize this as we have our objective, which you could write as some F transpose W, which is the actual feature matrix times the weights. That's going to give us our scores. So this is kind of like our score vector C. So we have this score vector C transpose Z, which are all of the indicator variables. And then we have constraints AZ is equal to B, or less than or equal to. Okay, so finally then we can treat this map inference problem as if it were a binary integer linear program. Okay, so looking ahead, we're going to use map inference as a subroutine within two learning algorithms, structured perceptron and structured SVM. And so the way that we had been doing learning up until now was maximum conditional likelihood estimation, right? Where we want to choose the parameters that maximize the log likelihood of the data. Okay, but then classification was potentially going to either look at marginals, or it could now do map inference where you could choose the highest scoring configuration. But if we're only doing classification with some dot product of weights and features, then this sort of begs the question, do we really need to learn the entire distribution? Right? We don't actually use the log of the partition function at classification time. Okay, so what we find is that, so if you train with a CRF, it does a lot better than if you train with, say, an SVM on the raw pixels. Okay, an independent SVM that just looks at one character at a time. That said, you can incorporate kernels into the SVM, like quadratic or cubic kernel, and then you can actually beat the CRF. Okay. Well, it turns out you could also do this, which is structured SVM. And it's also called a M3N. And the structured SVM can actually also support kernels. And so it can have the advantage of kernels inside the structured SVM. Okay. But you'll also notice that even if you're not doing kernels, the structured SVM does outperform the CRF. So 45% error reduction over linear CRFs. So here, this is yet another comparison where the structured SVM does better. This is on hypertext classification, where you're looking at connections between web pages. And then on named entity, where higher is better here, you can see CRFs are beaten by linear structured SVM. And then it's even better if you use sort of a quadratic kernel within a structured SVM. Okay, so next time, in order to lead into structured SVM, we'll talk about structured perceptron, which is sort of the natural stepping stone for the structured SVM. So see you guys then.